Hi, in this video we are going to talk about how we can deploy a machine learning model in a low power and low compute environment, typically what we call as edge of the device, right? It can be your industrial machinery, it can be your mobile phone, it can be a drone that is flying, it can be anything, like how you can deploy a model into an edge of a device. Now, what is so special about these scenarios? When we talk about edge of a device, right, they don't have the luxury of memory that our computer or our servers has. It does not have the luxury of CPU that our servers can run up to 96 core CPUs, but typically the edge of the device may have maximum quad core or octa core, right? So there are a lot of constraints that you need to take and deploy the model. And when we talk about a typical neural network model, it has lot of parameters, and finally the saved model will be multiple MBs, and even in sometimes it can be even GBs as well. So how can we make these kind of models more efficient that it can be deployed on an edge of a device, right? There are multiple names to it: edge analytics, there is like post-model quantization, there are like kind of weights pruning. Now these are all true to it, but edge analytics, when you talk about edge analytics, this is not the only way we can do edge analytics. Edge analytics is combination of even advanced analytics. You don't need a predictive modeling as well, but you can also deploy a predictive solution over there. So let's focus on how we can do it, right? So before going there, let's talk about some of the use cases of edge analytics. First of all, I have a detailed video on edge analytics, and if you want to know what is edge analytics, then you can click the link on the top. Like, some may feel these are like more bleeding edge technology. Not really. This is something like happening today, right? And we can see more and more instances and use cases coming out in the future. So you can click the link on the top I had given, and you can watch what is edge analytics. Now let's quickly talk about some use cases. The first is, if we know self-driving car, right? Autonomous vehicle. Now, if you see the typical autonomous vehicle, it has a lot of sensors attached to it. Now, if you a autonomous vehicle need to recognize the environment, the weather that car is driving on, where there's a pedestrian before, where there's a car in the front, backs, right hand side, left hand side. When it's taking a turn, it needs to know about the environment, or when changing a lane, it needs to understand signal, it needs to understand object. So basically, a autonomous vehicle contains nothing but an bunch of all sensors. It can be a combination of deep learning model or machine learning model running over there. Now, these are one kind of constraint devices, right? And when you are deploying a model, you want to keep the model as lean as possible. At the same time, you also want to make sure it is more accurate, right? When you are kind of cutting down the weights or pruning the weights, you don't want to lose the accuracy aspect of it. So we will see some scenarios how to do it. So this is one of the example. The second example is in the defense. So some of the countries have large border to maintain, and you want to make sure people don't infiltrate and everything. So can we use lightweight video monitoring devices over there that can alert in case of any activity in the border? So basically, you can take a model and deploy it in the via video system, and then it can monitor it, and if it finds any anomaly, it can more like alert the main station back. There is predictive maintenance today in industry, and outage in machinery can cause like a lot of production, basically production backlog. Now, they may have alternate machinery as well to compensate for it, but during a peak season, they want to continuously monitor the machinery, and if something happens to the machines, they want to get notified as soon as possible. So basically, these kind of models can be deployed inside the machines, so that like the model like monitors continuously the activity and data, and alert in case of an anomaly. Mobile device, or you can also take mobile device as an example, where you want to do some AI for good, right? There are a lot of people who cannot see small letters properly. Maybe you can deploy a model inside the mobile phone, and when they scan that particular text, it basically reads out, it just converts the text into speech. So a lot of people who are kind of disabled or not able to see properly can get benefited can get benefited by from AI. So we need some solution that can make it happen, and that's what we are going to talk today. Right. So let's get into the notebook quickly. Now I have mounted my collab drive, which has all the models as usual. If you have seen my previous video, you would have kind of know it. I'm going to list down my folder. So I have a lot of models here, and in my previous one I used the sentiment analysis, but in this I am going to use the fashion TPU model. This fashion TPU model was created using TensorFlow, and it is there in one of my videos where I am talking about GPUs and TPU training. In case if you want to go and see and run the model and save the model, you can just click the link on the top where I'm taking through like how to start with TensorFlow 2.0, how to run TensorFlow 2.0 on GPUs and TPUs, what distribution strategy to use. So you can use the link on the top and you can go over there and check it out. But I'm just going to take the output of the model and run it. Right, I'm importing all the packages that are required. The only thing I need is TensorFlow, but I'm just importing NumPy and Matplotlib to visualize the output. Right. So now TensorFlow is selected. So let me, yeah. So first thing what I am doing is I am basically loading the model as it is. Right. This is the model that we have, TensorFlow TPU. I am using the Keras load model, and then I am printing the model summary. It will give me like what is the model layers and everything. So you can see basically this model has around 1 million trained weights. There is a convolution neural network. There is another convolution neural network. There are multiple convolution neural networks and everything. But let me skip it. So, and there are around 1 million, close to 1 million parameters in the model. The very first thing I am going to do is I am going to use the TFlite over here. So basically TensorFlow Lite is provided by TensorFlow itself. It is designed to execute models more efficiently on mobile and other embedded devices which have limited compute and memory resources. Now, some of this efficiency comes from a special format that they use to store the models. Typically, they use flat buffers to store the model, and TensorFlow Lite is compatible with Android, iOS, or C, or even Swift or other languages. So basically, you can save the model in TensorFlow Lite, and then you can use the other libraries to deploy the model. Right, and the converting this model, you can see like how it reduces the file size. I will show that around, but converting the model reduces the file size, but it also makes sure the accuracy is not impacted. So that is the primary purpose of TensorFlow Lite. So let me quickly show that to you. So if you see here, TensorFlow, what I'm doing is I am from TF, I'm importing TensorFlow Lite converter, and from Keras model, the model that we had on the top, right? From the Keras model, I am loading the model object and then converting it to TFlite, and then I'm using the converter object.convert. So if I run this, it's going to take this model and convert it into more efficient storage provided by TFlite. Now, if you go on the top, the model size, the fashion TPU model size we had was around how much it is, 14 MB, right? It's around 14 MB. Now after the conversion, let's see like how much this particular model size is. So let me quickly, if you see the model size, this in KBs, so this become MB, it's 4 MB. So from around 10 MB of size, it has become 4 MB. So almost like it's kind of less than half the size, right? Now this is one part of converting it. Now I can further, when we do a TFlite, it just does a efficient storage. It does not, the accuracy will be mostly same. There will be some point, not 1% drop, but that is fine. That will not impact the output. The one more thing I can do is I can do post-model quantization. So what is post-model quantization is, it takes the output weights. Typically the output weights are stored in a float32 format. If you do a model.weights, it will show all the weights. You can see it's a float32 format. In this case, what I am going to do is, when I do a quantization, I am telling basically go and prune the weights, go and trim down the weights. So basically I can tell whether I want to cut down the float32 to float 16 or float32 to int 16 or int 8. So as I go more lower, the model becomes less in size, but at the same time you may see drop in accuracy as well. It's some drop in accuracy. So that's what the quantization does. So in this line, if you see, what I am telling is use the optimize method and optimize for latency. Now there are multiple methods to it. If you click on this, you will find optimize for latency, optimize for size, and default. So you can give any of the options. I have given optimize for latency. Now, and then I'm calling again converter.convert and contest, and again I'm saving it as a TensorFlow quantize model. It will further reduce the size, and we are going to see how much it reduces the size. By default, it's going to do a float 16. Now, if in case if you want to do even further down, I have commented out some lines. You can use it. You also need to pass a data set, because when it's trying to quantize it, it wants to make sure that the model, that the data it has seen also it's run across and see how it performs. So that's why it needs a data set. I'm not going to do that, but it's commented out if you want to do, and this for integer 8. If you want to do it in integer 8, you can do it. Here I'm just doing optimize for latency and then saving it. Now let me run this line, and then let's quickly see the size of the quantize model. So now if you see, it's only like 1 MB. So from the 10 MB model, the TFlite converted into around 4 MB, and now after quantization, basically it's around 1 MB. So it has reduced even further, right? Now, how does this model perform compared to our previous model? And if you want to know more about quantization, model quantization, again I have a separate video on that. You can go and look into it. It's a pretty detailed video. It's a short 3 minutes video, but it's a detailed video. You can click the link on the top and go and check about post-model quantization. There are other methods like quantization during training of the model, but sometimes like you train the model and do a post-model quantization, that is also an option. And the video I'm talking about is post-model quantization. And what we have done over here is post-model quantization. We have taken the model that has trained and then applying quantization. So that's what we are doing here, right? Now let's see how it performs compared to our regular model. So we have one model that is Keras model, and then we have one model that is TFlite model, and I'm going to use TFlite model to check the output. But if you want, you can just change the quantize model and also check the output. But let me quickly go and import the data set. I'm using the fashion MNST data set where it was trained on, and I'm going to use the test data set to evaluate the performance. The test data set has around 10,000 records. That's a good number to check the accuracy of the model. The first thing I'm going to do is if you see here, basically it has the number of instances, it has the height and width of the image. It does not have a batch dimension. We need the batch dimension because our model was trained using batch dimension. So I'm just expanding the dimensions to include a batch dimension, right? Now this is how I load a. So when you are deploying the model, you need to start from here, right? Now this is how I load a TensorFlow Lite model. This TensorFlow Lite model is nothing but the object that I have saved during the TFlite converter, right? I can also use the TFlite quantize model over there if I want to use the quantization model. But let me show you the TFlite model, which gave us from 10 MB to 4 MB size, right? So I am calling the TFlite interpreter. And then once the interpreter comes, I'm just allocating all the tensors from the output of the model. And what I am doing is I am getting the input tensor, which is the the model will have an input tensor and output tensor. Basically, input tensor is the data that we feed in. So I'm getting the input tensor from the interpreter, and I am also getting the output tensor where my final output will get stored after the model is after the model scores the instance. So this is what I am doing in this 4 lines. And this 4 lines is what you need to deploy a model. So if you are going to deploy on a Android device, just install a TFlite package and then you again get started. You don't have to install the entire TensorFlow library. Yeah, the entire TensorFlow library will be pretty big. You just have to install the TFlite, right? There's a Java version as well. You can use Java to also run TFlite. Right now, I'll quickly get the tensor details. So basically, it shows all the tensors that are there within the model, and see, I'm not using the quantized version, so it's telling the quantized is only 0.0. Right now, next what I am doing is I am printing all the layers just to see the weights. If you want to check the weights, you can check it. This is the weights from the TFlite model, and if you want to check the weights from the Keras actual model also, you can check, because internally in the model you want to make sure how the weight looks like. And when you do the same thing for a quantized model, you will see basically the weights are represented sometimes as hint, because it was able to optimize it for them. That's why the saving from 4 MB to 1 MB size. Right. Now what I'm going to do is I'm going to take all the images, right? The X-test data set, I'm going to take all the images, and then I'm going to basically call the interpreter. That the interpreter is basically the object, the TFlite interpreter that we are going to invoke the interpreter, and then we are going to kind of see the we are going to store all the output in the prediction output list that we have created on the top. So whatever the score is, the final fashion MNIST has 10 classes. So whatever class output is that, it's going to store that in the prediction output. Once we have the prediction output, in the next one what we are going to do is we are going to validate the accuracy. So here if you see, now I got this ran, so I have all the 10,000 images that I have. I am having the prediction score as a list. Here I am going to run to the prediction output. I am going to compare if the prediction output is equal to y-test, that means the model has predicted accurately, otherwise it does not. And then I'm finally printing my accuracy. So the accuracy is around 91.6%, and that was the same accuracy. If you have seen my TensorFlow training video, that's the accuracy we got in the model itself, right? So basically there is no loss in accuracy. And how can we make sure? Let's quickly go and visualize some 10 images from the test data set and see like how well it has done compared to the regular model. So what I'm doing here is I am basically running for 10 images, and I am going a plot.show images. I'm getting the actual label, which is the y-test data set. The TensorFlow regular model that we have, the TensorFlow model which we loaded in Keras directly, which did not have TFlite or quantization, I am printing the prediction of it. I am also printing the prediction of quantized model, which is the prediction output I used on the top. And let's quickly see how the data looks like. So if you see this particular 10 images, you can see the actual label is 7, and the TensorFlow regular model label is 7, and quantized model is also 7. And similarly, if you see on the top, the actual label is 5, TensorFlow regular model is 5, quantized model is also 5. Right, so basically there is no difference in accuracy over here. But in case if you are using the quantized model, you may find some accuracy difference. Maybe in thousands of images you may have like 0.01% where it may not be same, because when you are training the weights, it may not highly impact your image model or text model, but it can impact your model. If you are running a neural network on tabular data, you can see some impact, but otherwise it's not going to be of a big impact to you. Right, now let's benchmark the time it takes. I'm going to take the 10,000 images and run it with the quantized model and also with the final what do you call the Keras model. Right, so first I'm running with the quantized model, and the quantized model, what I'm doing is I'm taking all the 10,000 images, the X-test 10,000 images, and I'm just calling the interpreted or invoke, and I'm just printing the total time it takes. I'm taking the start time here, between the start time and end time, how much time it takes for the 10,000 images, and you can see it actually takes 19 seconds. Right, now let me do the same thing for the Keras model. In this case, I am using the model.predict function of Keras. So this is a regular model, so I'm not going to wait till it completes, but you can see the time. I just saved the time here. It takes around 305 seconds. So basically this is almost like if you take this time, is almost 20 times or 18 times more than what the TFlite output is. So the point is like when you're deploying on the edge of a device, you want faster inference, and because you are running a low compute environment, and at the same time you need a lesser model size because you're deploying in a low memory device. And TFlite converter along with the quantization of model can give you a very lightweight model of your regular model. You're not doing anything, you're just taking the model and doing a post treatment to it. And also the runtime can be substantially increased, because when you're deploying on edge of a device, you want to immediately detect and send the response back. right? So this more about quantization. The quantization can also work on GPUs. So if you have a GPU device on your edge device, like you have a edge TPU or any of edge GPUs or something like that, you can also use GPUs to do your padding, which will increase your runtime even faster. Now, in a future video, what I'm going to do is I'm going to take a similar model, a quantized model, and maybe I will deploy it in a Raspberry Pi and show it to you. But that's going to be later in time. But this should give you pretty much to practice. And if you want to try with Android app deploying this model, there are a lot of documentation on TensorFlow website. You can go and check it out. Yeah. Thank you.